So welcome guys to my channel. Today we're going to talk about the application of integration. But there are two types of application of integration that we must tackle. So first part is areas and the second part is volume. But now let's just talk about area. So area has two types. First is under the curve. Under the curve. And second is between the curve. First, we're going to talk about the area under the curve. So let us illustrate what the area under the curve looks like. So this is our y axis and this is our x axis. So our origin here is 0. So area under the curve has been bound as a boundary from points A to B. So example, this is our area under the curve. So this line here is just equals to y of f of x. Now this area is what we should be investigating or solving. So first we put a point here to indicate that this point is from x to y and this point is our vertical strip. So from the origin to this point here is called x, and the thickness between the area of vertical strip is called dx, and the height of our dx is just equals to y. So by putting this out, our vertical strip is called the differential area with y and dx. Oh wait, no. This is, let me draw it again. This is y, this is our vertical strip. So this is dx and y. So this differential area is just equals to y dx, and the integral of area is just the integral of y dx. So this is our formula for area under the curve. So again guys, let me remind you something, that do not memorize the formula, just familiarize yourself with it. Now we're going to have our first example. So our first example is equals to, our first example is find the area under the line y is equals to, let's say 4x plus 2 from x equals to 0 to x equals to, let's say 5. Now we are going to illustrate our area. Oh, this is not straight. So illustrating, this is x axis and this is y axis. So our point here bounded with area is equals to 0. Let's say this is 5. So now how are we going to plot the line here? let me teach you from what I learned from my teacher. So first here we are going to make a tabular table. This is x and this is y. So if x equals to 0, our point here is just our y, 4 times 0 plus 2, our y is equals to 2. By the way, I'm referring to this line here. Now, in plotting points in line, we must have 2 points. So if x equals to 0, we already got the y, and if x equals to 1, our y here is 4 times 1 plus 2 is just equals to 6. So let's plot the points. So if x equals to 0, our y, let's say this is 2, and if x equals to 1, our y here is, let's say this is 6. So by 0 to 2 and 1 is to 6. We put this closer so it won't look awkward. So our line here, we put erase this a little bit. So this is 1 and this is 5, 1, 5, so point, and the area is this, bounded from the point 0 to 5. So let's say this bounded. Now this is y, our line here is equals to y equals to 4x plus 2. Now here we are going to put a point here for equals to x equals to y, and we put our vertical strip. So the point of origin to this point below the vertical strip is called y, or x, and the height of our vertical strip here is just equals to y, and the thickness of this area is equals to dx. So now we move this area, this vertical strip I mean here. So this is called differential area. So differential area is equals to y. No, first we draw our vertical strip. This is y and this is dx, and this is called differential area. Our differential area is just equals to y dx. So the integral of area is equals to the integral, our limit here, first our y here is equals to 4x plus 2 dx. We'll substitute the y to our equation, which is 4x plus 2. Now the limits here is from 0 to 5. So 0 to 5. Now by solving this, let's put it here. Area of the integral of 4x plus 2, let me mentally solve it. So 4x, 4, then x squared by using the power formula over 2 plus 2x from limits to 5 and 0. So by simplifying this will cancel out, and this will have 2, and this will become 2x squared plus 2x from limits to 5 and 0. So by substituting the upper limit and lower limit to our x, our answer should be, by substituting this is 5 raised to 2 plus 2. For x here is 5. So 0, so by substituting 0 to this rest of the equation, our answer is 0. Upper limit minus lower limit. So our final answer here is 5 squared is 25 times 2 is just 50 plus 2 times 5 is 10. So 50 times 10 is equals to 60 squared units. So this is our answer from our first example under the line y equals to 4x plus 2 from x equals to 0 to x equals to 5. Now moving on to example number 2. So example number 2, find the area from y equals to x squared of x, area under the curve, area under the curve y equals to square root of x from x equals to 0 to x equals to 5. So now by illustrating this is our y, and this is our x-axis. Let's put it here so we can use a space here. So from x equals to 0 and x equals to, let's say, 5 here. So now how do we find the points of our y? So by doing this, our line here, our curve here is just equals to, let's use the tabular method, x and y. So if x equals to 0, so square root of x, this is equals to 0, and if our x equals to 1, our y is also 1, and let's say our x equals to, let's say, 4, our y is equals to 2. So I recommend you guys, by plotting the tabular method from x to y, our x here should have, when example here, let's say our x equals to 3. Let me show you my calculator. So square root of 3. So there is no value, which is no whole number, I mean. So I recommend you guys to put in a value that has a whole number when substituting. So by plotting in the points, x equals to 0, y equals to 0, this is our first point. 1, here x equals to 1. Let's say this is 1, and this is also 1, and x equals to 4, and our y is 2. So by plotting in the points, this is the point that we should have from here to there and here to here. So by connecting this, it should look like this. Erase this. It should look like this. So let me erase this first. So our line here is just equals to y equals to square root of x, and this line, in this area, I mean this curve, is bounded by points 0 to 5. So this is our area. Now we're going to put a point, let's say here, and this is just our vertical strip from x, y, and from the origin to this point here, from the vertical strip, this is x, and the height of this vertical strip is just equals to y, and the thickness here equals to dx. Now we are going to take out this strip, our vertical strip. So this is just our vertical strip, and this is y, and this is our dx. So as you guys remember, this is our, so I put it here, differential area. Our differential area is just equals to y dx. And now the integral of area to y dx is just integral area is equals to integral of from limits to a to b y dx. So by substituting y, our y here is y square root of x. So the integral of y square root of x, square root of x dx from limits to 0 to 5 in respect to dx. So 0 to 5. So now let's put it here. Our answer for this problem, now we're going to integrate it, is, let's change square root first. So x raised to 1/2 plus 1 over 1/2 plus 1. So this is just equals to x raised to 3/2 over 3/2. Now by reciprocating this, our answer here is 2/3 of x raised to 3/2 from limits to 0 to 5. So we put it here. So 2/3, by substituting x to our limits here, x is 5 raised to 3/2 minus, so by substituting 0 here, our answer is 0. Now our final answer should be, well, let me get my calculator. So our answer here, by plotting in the values, 2/3 times 5 raised to 3/2, our answer is equals to 7.45. 7.45. So 7.45 square units. Now this is our answer to our example number 2. Now next we are going to tackle about area between the curves. So now we are going to tackle or teach you how to solve area between the curves. So let us put our illustration first. This is y, and let's just put here x. There is that. Is that straight? It's x. So if our line here, our area, has two curves, first curve is this, and another curve is, let's say, this parabola. A parabola, but only half of it. So let's put it here. Now this is our 0, and from points A to B. Oh no, that's wrong. So now imagine if our curve here has two, so area between the curves has always two curves that intersect with each other. So let's say this is our first curve, y1 is equals to f of x, and this is our second curve, let's say y2 is equals to f of x. Now our area of interest is here. Now we need to plot a point here, and let's say we do a vertical strip. So our area here from this point origin to this point is just equals to x, and this is just equals to the height of this equals to y. So what about this point and this point? So let's first erase that. So this point is just equals the one touching the bottom of the vertical strip. It's labeled that as our y2 since it touches the bottom of our vertical strip. Let's put that y2, and this in this line touching above the vertical strip is our y1. So the area here, say this is area, where is this? The area here is just the difference between the two lines. So first, by doing the difference, we must first put the bigger area minus the lower area. So another method is y upper or y lower, but in this case I will label it as y1 minus y2 since y1 is bigger than y2. So now taking this vertical strip outside, this is our dx. I forgot to put here dx. This is our dx, and the area here is just equals to y1 minus y2, and the differential area of this, let's put it here. Our differential area is equals to y1 minus y2. So it depends on you what is the first y, or what is the first curve that you will label as y1 or y2. So y1 minus y2 dx. The integral of this area between the curves is just the integral of y1 minus y2 dx from limits to a to b. So this is our formula for area between the curves. So now let's have our first example. So our first example is find the area between the curve y equals to x squared and y equals to x. So let me first illustrate it here. It's our x and 0 is our origin, and this is our y. So we don't know the points of this or in this line or curve. So what we will do now is to equate y equals to y equals to y. So it is just x squared equals to x. Then let's transfer x here, x squared or x here, and let this equate to 0. So 0, or let's say x squared minus x is equals to 0. Now we factor this equation here. So the common factor here is x. Now x equals to x minus 1 equals to 0. So now our x here, so by equating x to 0, our x equals to 0 and x minus 1 equals to 0. Our 2 point of x here is just x. Let's transfer negative 1 to here. So x equals to 1. So this is our points for our x-axis. So x equals to 0 and x equals to 1. So x equals to 1, this is 1 1, this is 1 1. So 0 by equating x here, creating a tabular method. If x equals to 0, our x here equals to also 0, and x equals to 1, our y here is just equals also to 1. So it is both the same when y equals to x. So let me erase this part first. So our point here is from 0 to 1. Oh no, let me, okay, so our point here is from 0 to 1, 0, then 1 to 1. Now this is our first line. So y equals to x squared is a parabola. So let's input that here, 0 to 1. No, where is that? 0 to 1. First we put our parabola 0 to 1, then our line here from 0 to 1. Oh, let me make it bigger. So this is our 1 and this is our point 0 to 1. This is our line and this is our parabola. So this line is equals to y equals to x, and this line, this curve or parabola is equals to y equals to x squared. So now this is our area of interest. So by plotting a vertical strip here, this is our point. So vertical strip, this is equals to x, and this is our dx, and this is x and y. So this area here is our, its label is as y1 and y2. So the curve touching the below the vertical strip, let's name that as y1, and the area here, let's label that as it touches the line here, y2, let's label as y2. So our difference here is just bigger minus smaller, or upper minus lower. So y squared, let's put it here, y squared minus y1, and let's put our vertical strip outside. So this is our vertical strip, and this is just y squared, y2 minus y1, and the dx. So the differential area of this is just equals to here, the y1, or y squared, y2 minus y1 dx, and the integral of area is just the integral of y2 minus y1 dx from limits to 0 to 1. So by replacing y to our equation here, y2 is x. So integral of x minus our y1 here is x squared, x minus x squared dx. So now we are ready to integrate this problem. So the integral of x is just equals to x squared over 2 minus x cubed, 1 here, let's put this 2 plus 1, power formula, x cubed minus 3 from limits to 1 and 0. So our area here, by substituting here, our 1 half, 1 raised to 1 just 1, minus 1 raised to cube is just 1, 1 half minus 1/3 minus 0, because 0 over 2 is just equals to 0. So by simplifying this for even further, our answer here is, let's say, let's put here, and 3 minus, first multiply 2 and times the denominator 6. Our answer here is 1 over 6 square units. Now this is our answer for our problem number 1 for area between the curve. So for our number 2 problem from finding the area between the curves, our number 2 problem is find the area between the curves y equals to square root of x and y equals to x. So first we need to form a tabular table. So this is a tabular table for y equals to square root of x. If x equals to 0, y also equals to 0. If x is equals to 1, y is also equals to 1. And if x equals to 4, so guys, a quick reminder, from picking out a value when y is equals to a square root, you must pick a value that its y is equals to a whole number. So I picked 4 here, so the square root of 4 is just equals to 2. So now we're plugging in the values. So 0 to 0 is 0, 1 is to 1, say 1 is to 1, and 4 is to 2, 4 is to 2. Now by plugging in the value. So later we're just going to get the intersection of between these two curves. So first we are going to get a tabular method for this line right here. So if for x and y, f equals to y. So if x is 0, y is also equals to 0, and if x is 1, y is also equals to 1, and if x is 2, y is also equals to 2. So the point of intersection here is from 1 to 2. Is from 1, x is 1 and y is 1. So they both intersect this. So let's do that. First we input these points. So x equals to 0, 1 equals to 1, 2 is equals to 2. So this is 2. So our point of intersection is this. And this. Let me erase this. So never mind these points here. This 4 and 2. Let's just focus on the points of intersection. But first, let me rewrite this. Erase this. Let's make it bigger. So 1. Erasing it. Put here point of intersection. 1. Then we have a point here. So equals to 1. So our area of interest is here. Now we label this. First line is here y1 is equals to square root of x. Then our line here is y equals to x. So now from this point, this is equals to x. First let me put a point here and make a vertical strip. So from this point, the lower, touching the lower vertical strip, let's label that as y1, y2. Let me erase that. Y2 plus 2x. So let's put it y2 because the line that is touching the lower of the bottom of the vertical strip is y2, and the area of this point is just equals to y1, and then the area between them is just y1 minus y2, and thickness here is dx. So now let's take out this vertical strip. So now the vertical strip is just y1 minus y2 dx. So by taking this is the differential area, or dA, equals to y1 minus y2 dx. So the integral of area of y1 minus y2 dx from limits to A to B is equals to, let's put it here, and let's substitute the values of each letter here. y1 here is just integral of y1 here is square root of x minus y2 here is x dx from limits to 0 to 1. Why? Because from along the x-axis or dx we must respect x to dx, so 0 to 1. So now the answer of this is just by integrating this x raised to 1/2 plus 1 is just equals to 3 halves over 3 halves minus x squared over 2 from limits to 1 and 0. So by simplifying this further, this equals to 2/3 x raised to 3 halves minus x squared over 2 from limits to 1 and 0. Let's put it here. So area by substituting the x here to the upper limit and lower limit, so that becomes 2/3 1 raised to 3 halves minus 1 raised to 2 over 2 minus 0 here is just 0. So by the final answer is 2/3 minus 1/2 equals to, let's say here, 2 times 2 is just equals to 4, cross multiply, 3 times 1 is equals to 3 over the denominator, which is 3 times 2 is 6. So the answer here is just 1 over 6 square units. Let me check my calculator to confirm it. So 2/3 here. So 2/3 minus 1/2 is equals to 1 over 6. So we're right. So that is all for the area between the curves. Now we are going to tackle volumes. See you on my next lecture. Thank you and have a nice day. So good day everyone. This is still under the area of integration, so name polar curves. So polar curves, first we need to graph this. So if this is our line here, this is the area of interest, and the line bounded here is just equals to r, and also this is equals to r, and the strip here looks like this. Strip here look like this. So this looks like an sector of a circle. So first we draw a circle in order for you to understand. This is our circle. No, this is an oblong. So this is our circle here. When divided into different parts, this area is called the area of the sector of the circle. So this is just equals to area of sector just equals to 1/2 r squared theta. So 1/2 r squared d data from limits to theta 1 to theta 2. So this is our formula for polar curves. So now let's move on to our first example here. Find the area of r equals 3 sine theta. So first, we need to find the theta. As I already put the theta here, the theta is equals to the angle of the graph. Let's say this is the angle, this is the graph. So we all know that this is 0 degree, this is 90 degrees, this is 180 degrees, and this is 360 degrees. So by putting a circle here, this angle is equals to 30 degrees. This is 60. This is, let's say, 90, 120, 150, 210. Let me erase this. 210. This is 240. This is not 360. This is 270. 270. 300, 330, and 360. The whole circle is a 360. So now we have our theta here, or the angle of each value. So let's erase this first. So by solving polar equation or polar plane, polar equation, we need to input the value of our r into our calculator here. So by setting the mode, let me show you. Mode here is the comp, so we must put the mode in table. So f of x here is just equals to 3 sine x. X. So equals, we start with 0 and then we end with 360, and the step is just 30 because our angles comes from 0 to 30, 60 to 90. So the common difference is 30. So let's put 30 here. Now we have here the values of our r. So if x equals to 0, theta equals 0, our r is equals to 0. R equals to 0. And if 30 is our theta, this becomes 1.5. This becomes 2.6. 90 here. 90 here is just plus 3, 120 equals 2.6, 180 is 1.5, 210 is negative 1.5, 240 is negative 2.6, 2.6, 270 here is negative 3, 300 here is negative 2.6. Oh no, yes, 2.6. 330 here is negative 1.5, and 360 here equals to 0. Now we are ready to plot our polar plane. So let's do that. Let's put it here. So our biggest radius here is 3, so we need to put 3 circles. So this is first circle, our second circle, and our third circle. Let me erase the second circle. So by first by putting the values of how to solve the r here, we need to put our calculator into degree mode, and later when we are about to integrate, we will put our calculator in region mode. So here, so let's start. If 0 theta, the angle r equals to 0, this is our first point here, first point. So if 30, let's do 30, let's draw first the each angle. So it's not perfect, I'm sorry. So this is just equals to, this is 30 degrees, 60 degrees, 120, 150, 210, 240. This is not 360, this is 270. This is 300, and this is 330, and 360 is just equals to 0. So it is a complete revolution. So first here, our theta is equals to 0 and our r 0, so we put radius here 0. Then 30 here, its r is 1.5, so let's estimate here. This is 1, this is 1.5. Let's put it here, the middle. Can you see it? Let's make it bigger here. And 60 is 2.6, so this is 2. First circle, second circle, 2. Let's put it here. 60 is 2.6, let's put it here. And 90 degrees is 3, so in the third circle. 120 here is 2.6, let's put it here. 150, first we need to connect the dots. So 150 is, so 150 here. Oh no, I forgot to put 150. Wait, let me try again. 3 sine of x from 0 to 60 from 30. This is 150, 150, 180. So 150 here is equals to 1.5. This is 1.5. 150 is 1.5. Yes. And 180 here is just equals to 0. Okay. Now 210 is 150. Now moving on. 150 here is 1.5. So 1.5 is 50. 1.5. Let's put it here in the middle. Let's assume it. So 180 is 0. So let's put this here. So our area looks like a circle, but we need to finish this first. So 210 here is negative 1.5. So 210 here, this line here is positive. So at the end, so at the opposite, this line here is just equals to 210, negative 1.5. Here, negative 1.5. So it's still the same. So 240 is 2.6 here, 2.6 is here, and 270 is negative 3. So this is positive. This line is positive. So the opposite of positive here is negative. So we put here 3. The circle is here. So by inspection, our area is here. this covers two areas. So let's put it, first we need to put the differential area. Let me change my color. Differential area. Differential area is just equals to 1/2 r squared d theta. So the integral of area is just equals to integral of 1/2 r here. This is substitute r. So r here is 3 sine theta. 3 sine theta squared d theta. So by finding the limits here, our limit starts with 0 and ends with 90. Yes, 90 here is just equivalent to pi over 2. So let's do that. 0 to pi over 2 times 2, because this covers 2 area. Okay, so area equals to 2 times the integral of 1/2. Let's simplify this. 3 sine is equals to 9 sine squared theta d theta, from limits to 0 to pi over 2. So now we are ready to integrate, but first 2 and 1/2 we just cancel each other. So what we will left is 9 sine squared theta d theta, from limits to 0 to pi over 2. So this is just equals to, by calculating our calculator here, by using our calculator, the integral of pi over 2, limits of 2, from the value of 9, say 9 sine squared x. Oh no, wait a minute. So let's do it again, our calculator. So then the integral from limits to pi, here's pi over 2. Oh, I know why, because I know why where we are wrong. We forgot to put the mode to radian. So as I said earlier, by inputting the values of finding each value of this polar area, we need to put our calculator into degree mode, and while finding the integral, we need to put our calculator to radian mode. So let's do that. Mode radian. So our mode now is equals to radian. I mean. So now we are ready to integrate. So pi over 2, 0, and the value of 9, of course 9 sine x squared. So our answer here is just equals to 9 over 4 pi square units. So this is our answer for our number 1 problem of area of R equals to 3 sine squared. It's 3 sine theta. So now we move on to number 2, our last example. Find the area set to table mode here. So our f of x here is 3 cosine 3x. Cosine 3 cosine 3x. So let's start with 0 and we end with 360 and the step is 30. Oh no, it's negative. Let me change to another equation. Oh, this is correct. So this is correct. Our equation here is correct. So the fault is our calculator because we forgot it to set into degree mode. So quick reminder to all my viewers, when calculating this type of equation, this type of solution, we need to put our calculator here into degree mode. So let's do that. So I already set here my calculator to degree mode. So degree is our function here is 3 cosine 3x. Start with 0 and with 360 and the step is 30. So if 0 here is equals to 3, so this is 30 is 0, it's negative 3, 90 is 0, is 3 is 0, is negative 3, 180 is negative 3, 210 is 0, 240 is 3, 270 is 0, is negative 3, 330 is 0, and 360 is 3. So now we are ready to plug in the points in our plane area, our polar plane, polar plane. So the value here, the radius here is equals, the highest radius here is 3, so we need to form 3 circles. So circle number 1, circle number 2, and circle number 3. Let's erase this. Circle number 2, circle number 3. So this is 0 degrees, 90 degrees, 180 degrees, and 270. I mean, I always forget that. So now we need to form here 30, 60. This is 120. This is 150, 180, 110, 240, 300, and 330. So now, if our angle here is 0, our R becomes to 3. So put it here first. Our first point is here. First point. If our 30 degree here is equals to 0, this put it in 0 here. 60 is negative 3, so we put it negative 3 here, the opposite. So this line is positive and the opposite of that is negative, so we put it here. 60, negative 3, 90 is just 0 here. So we need to form here the line. This what look like. So 150 here, 120 is 3, so 120 is 3. Let's put it here, 120. 0. 150 equals to 0 here. 180 is negative 3, so we put it negative 3 here. So by first we need to connect the dots. So 120, we end with 240 negative 3. 60 is negative 3, 0, 0. Then we put it here 0. 0 here. 123, 150, 0. This is 0. 180 is negative 3. Let me get my cell phone here, and we use our GeoGebra to double check. So if y is equals to 3 cosine of 3x, 3 cosine 3x. So again we plot our points again. So if 0 equals, if 0 here, our r is 3 here. This is 3. If 30, this is 0. If 60 degrees is negative 3, put it here. And 90 is equals to 0. So this forms this. 90 equals to 0. Forms like this. 90 equals 120 equals to 3. This forms this. 150 equals to 0. This forms this. 180 is to the negative 3. This is form this. And 210 is 0. This form that. 40 is 3. That. And 270 is 0. And 300 is negative 3. 300 is negative 3. So by inspection, this looks like this. Let me look better, clearer look. So this forms like a that. No, this forms like an electric fan with 3 blades. So our differential area here, we just need to put a point here from 0 to 90, 0. So a point here, we put a point here. Put a point here. Our strip here. By putting that outside, this is just equals to differential area equals to 1/2 r squared d theta. So the integral of this is just equals to 1/2 integral of 1/2. Let's substitute r to our original equation, which is 3 cosine of 3 theta d theta. From limits 0 to 0 to, let's say 0 to pi over 2. 90 is pi over 2, pi over 2. So area is equals to this just covers 1, and let's say put 4 here because it covers all the area. So let's put 4 here. Integral of 1/2 3 cosine of 3 theta squared. Oh, I forgot, this is squared. Take out 3 outside, so 2 times 3 is just equals to 6. 6 integral of, oh no, we forgot to put to square it, so 9 times 2 is just equals to 18 integral of cosine of 3 here. Cosine of 3 cosine of 2 cosine of, this is 2 cosine squared of 3 theta d theta from limit to 0 to pi over 2. So now we integrate. So first we need to set our calculator into region mode. So let's do this mode, mode computation degree, shift mode into rad. So the integral of, let's put 18 here outside. 18 here is just 2 times 9, so 18 is pi over 2. So pi over 2 from limit to 0, and cosine of 3 x dx. Now we put equals, we enter equals. Our answer here is equals to negative 6. Maybe I'm wrong in my 2 graph here. Another graph here. 40 plus 3. So our answer here is negative 6 square units. So this is our answer for problem number 2. That's all, and see you on my next lecture in volume. So good day again, everyone. Today we are going to talk about part 2 of application of education, and that is volumes. So volumes has 3 methods. First is the disk method. Second is the shell method. and the third is the washer method. So for today's lecture, we are going to tackle these three methods. But first, we are going to learn what is the disk method. So let's start. It's a disk method. So first we need to illustrate or create a graph. This is the graph. So this is our y-axis and this is our x-axis and this is our point of origin. Let's say we have a line here. This line is just equals to f of x, y equals to f of x. Now let's say this line is bounded by the area between points A and B. So now this is our area. Now we put a point here and that is our vertical strip. Say point here. So this is a point here and this is our vertical strip. Now this area to the point of the bottom of the vertical strip is called our x, and the height of this vertical strip is just our y, and this is our x and y. So by rotating this vertical strip, and where is our area of area of rotation. Now if we rotate this vertical strip, see that this form a cylindrical disc. Now let us take out that cylindrical disc. Let's say this is our cylindrical disc. Let me erase that. Oh no, it's not straight. Let me erase it a little bit. Sorry, I don't know how to form a cylindrical disc, but let's say this is our cylindrical disc and this is our area of rotation. So if this is our y and this is our dx, so let's say first we are going to make a cylindrical disc. So this is our cylindrical disc. So let's say this is our cylindrical disc and this area here is just our radius. So cylinder. So this area is just our radius and this area is just our height, and this area is our and this part is our area. So by relating that to our cylindrical disc, let's erase it. Our cylindrical disc here is just a, let's say this is y. Our y here is just equals to the radius, and our dx here is just equals to our height. So by formulating the differential volume, differential volume is just equals to pi y squared dx. First, let's recall the formula for cylinder. So the formula for cylinder is just equals to the formula for the volume, of the cylinder, is just equals to pi r squared h. So in this case, y here is our radius and our height here is our dx. So by integrating this volume is just equals to the integral of pi y squared dx from limits to a to b. So this is our formula for the disc method. So now let's move on to the examples of our disc method. So example number one is find the volume if the area under the line let's say y equals to 2x plus 1 from x equals to 0 to x equals to 3. That's 3. So we need to do a graph to illustrate our process. Let's say this is our graph. Now this is our y-axis and this is our x-axis. So from x equals to 0, let's plot that first, to x equals to 3. Let's say this is 3. Now we are going to find the points here of our line. So let's use the tabular method. So x and y. So if x is 0, our y will become 1. And if x is, let's say, 2 or 1, let's say x equals to 1, our y here equals to 3. So now we have our 2 points. So let's plot that. If x equals to 1, if x equals to 0, our y is equals to 1. And if x equals to 1, our y is equals to 3. So let's plot the value. Let's plot the points, this 1, 0 to 1. So this will be this will be our values. Let's move that. Let's move it here. There. Wait. It is not straight. Let's say that is our line, and our line here is just equals to y equals to 2x plus 1, and this is the limit. 0 to 1 and 1 to 3. Oh no, I think it's here. It's not. Let me erase this. 1 to 3. Let me erase this 4 bit. Let me make it more bigger. So it's RX. Erase this. This is 1 and this is 3. Our limit is from 0 to 3. So now we're ready to just put it here. Let's move this to make it clearer. This is 1 and this is 3. Say this is 3. So from point 0 to 1, from okay, let's say this is our illustration. Our line here is just equals to y. Let's put it here, y equals to 2x plus 1, and this is our area of interest. Then we put a point here, say here, and then we draw a vertical strip, let's say right there, and from this point to origin to this point, the bottom of the vertical strip, this is labeled x, and the height of this is just equals to y, and the thickness here is just equals to dx from x equals to y. Now if we rotate this will become a cylindrical disc. First, let's put this out. This will become a cylindrical disc. Is it clear? Cylindrical disc. Then it's our cylindrical disc. Let me erase some portions here to make it clear. Let's erase that. Now we need to make a circle again, and this is our cylindrical disc. Now let's take this cylindrical disc outside. So no, not that. So let's say this is our cylindrical disc, and this is our area of rotation, or AOR. Then we plot the function. So if this is y, so this is our y, and the thickness here, or the height, is just equals to dx. So now the differential volume is just equals to pi y squared dx. So the integral of volume is just equals to integral of y squared, pi y squared, I mean pi y squared dx. So now let's substitute each of them to the original equation from limits to a to b. So our y here is just equals to 2x plus 1. So volume is just equals to the integral of pi 2x plus 1 squared dx from limits to 0 to 3. 0 to 3. Now first we need to take out pi outside. Now pi to become our process a lot more easier. Pi the integral of, let's expand this, so 2x times 2x is equals to 4x squared plus 4x plus 1, right? So let me put here 2x plus 1 times 2x plus 1. This will become 4x squared, will become 2x plus 2x plus 1. So our mental solution is correct. So from limits to 0 to 3. Now we are ready to integrate this. So this is just equals to pi. The integral of this and of this 4x squared is just equals to 4/3 x cubed plus 4x squared, 4 times x squared over 2. 4 and 2 will just cancel out, so what will happen will come 2x squared plus 1 plus 1 is equals to, let's say, x from limits to 0 to 3. Now we substitute x here to our limits, so this will become pi times 4/3 times t raised to cube plus 2 times 3 raised to 2 plus 3. So by getting our calculator here, let me show you my calculator. So this is just equals to 4/3 times, you see it, 4/3 times 3 raised to 3 plus 2 times 3 raised to 2 plus 3. So our answer is 57. 57 times pi is just equals to 57 pi. 57 pi. So volume, take note, volume is cubic units. Let's say 57 times pi. Yes, this is equals to 57 pi cubic units. So this is our answer for example number 1 from line y equals to 2x plus 1 from x equals to 0 to x equals to 3. So now moving on to our second example. Let's say determine the value of the area under the curve y equals to x squared plus 2 from x equals to 0 to x equals to 5, rotating in the x-axis. So first we need to illustrate, so let's do that. So this is our y and this is our x from point 0 to 5. So how do we get the vertex of the parabola here? So this parabola is opening upwards, so First, we are going to differentiate the parabola. So y prime is just equals to the derivative of x squared plus 2 is just 2x. So now let's just equate x to 0, and then ry will become to 2. So 0 squared is just 0 plus 2 is equals to 2. So let's plot in the value 0, and let's say this is 2. So this is our vertex. Now we need to find the points of the parabola by creating a tabular table. Let's see. So 0. So erase this. Let's say 0 here and 2 here. If x equals to, let's say, -1, ry will become 3. Yes, -1 squared is just +1 plus 2 equals to 3. Same with 1 here. Our 1 squared is just equals to 1 plus 2 is equals to 3. So this is our points of the parabola. So let's input that. So if x is -1, so if x is equals to -1, let's say this is -1, ry here is equals to 3. Oh no, ry here is equals to 3, and this is the point, and x here is 1, and the y is 3. So this is our parabola. Let's erase this for a minute. This is our parabola. Oh no. Let's put it here. Oh, this is 1. So our only interest here is from 0, from x equal to 0 to 5. So let's put that here. So let's say this is our parabola, and our parabola is y equals to x squared plus 2. So this is our area of interest. From x equals to 0 to x equals to 5. This is our interest. Let's say we put a vertical strip here, and then we label it from the origin to the point here is equals to x, and the thickness of the vertical strip is just equals to dx, and this is y. So by rotating this area of rotation, by rotating this, we can form a cylindrical disc. And say here, let's take out this cylindrical disc. Let's erase this for our space to use. So cylindrical disc, so this is our cylindrical disc, and the area of rotation is here. This area is just equals to y, which is our radius, and this is just equals to dx. Dx here is the height of our cylindrical disc. So the differential differential volume just equals to pi y squared dx. So volume, integral of volume, which is equals to integral of pi. Let's substitute y to the original equation, which is x squared plus 2 dx from limits from 0 to 5. So now we are ready to integrate this problem. So let's put it here. Volume is equals to pi. Let's take pi outside. The integral of x squared plus 2 dx from limits to 0 to 5. So by integrating this, our answer, by doing mental, this is just easy because we need to do is just the general power formula. So this is just equals to pi x cubed plus 3 plus 2x from limits to 5 and 0. So by plotting the limits to x, our problem will look like this: 5 raised to 3 over 3 plus 2 times 5 minus 0 here is just 0. So by putting this to our calculator, our answer, can you see on a calculator here? So let's say 5 raised to 3 over 3 plus 2 times 5. 2 times 5. Our answer here is just 155 over 3 pi. So pi times 155 over 3, say times 5 times pi. Our answer is just equals to 155 over 3 pi cubic units. So this is our answer for our problem for our disk method. And now next we are going to talk about the shell method, which is the second method for our volume using integration. So this is what we'll tackle next. So see you on my next video on volume using the shell method. So welcome back, and today we are going to discuss washer method. So washer method, first we need to illustrate here. As I already illustrate, now we need to put here the points where the area is bounded. So let's say that here, and this is the area of concern, and we put here x and y. So from this point, first we need to make a vertical strip there, and from this point to this point, this is called x, and the height of this vertical strip is just equals to y. And the thickness of this vertical strip is equals to dx. Now what if we have a line here, and this is called, let's call this b, and let's call this y equals to b, and this is our area of rotation. So first we need to put here a circle. So by doing this, we can make a solid solid shape. So circle here and circle there. Now by taking this out, this will become the shape here, and let's say this is the take it back. This is the area of rotation, AOR, and this part here is called X, and this from this part here to here is just equals to B. So from this part to this and to this part, this is called B, and this is called the area here equals to Y. So the differential volume of this is just equals the difference of the bigger area minus the lower area, which is B minus Y, and the formula for that is the differential volume is just equals to the pi of B squared minus B Y squared. So forgot this is our dx here, dx. So by the integral of that is just equals to the integral of B squared pi B squared minus B minus Y squared dx. So now this is our formula, and let's proceed to our equation to our problem number 1 here. So find the volume y equals to x squared and y equals to 2x. So we have two different curves here. The first curve is a parabola, and the second equation is just a line. So first we need to solve the points of our parabola, which is equals to x squared. The differentiation of that is just equals to 2x. Now let's equate x to 0 and y will become 1. Yes, so 0 and 1. X is 0, or vertex here, and y equals to 1. So let's erase that out. But before we erase that, we need to find the other points of the parabola by creating a tabular table here. If x equals to 0, y equals to 1. If x equals to negative 1, our y here will become 2, and x equals to 1, our y here will also become 2. So 1 and 2. So let's do that. So if x equals to negative 1, our y becomes 2, and x equals to 1, our y is equals to 2. So this is our points for our parabola. Never mind this part, just this right side only. So put a curve there. Now we are going to find the points of our line, which is y equals to 2x. So by putting a tabular table, if x equals to 0, our y becomes 2. Or 0, I mean, sorry, 0. And if x equals to 1, our y here become 2. So we have now our points for our line. So 0 and 0, and 1 and 2 here. So by putting that, oh no, 1 and 2 here, So by putting this line, let's make it bigger. So let's put 1 here, 1 and 2. This is our 2. So by putting that, this is our area of interest from limits to 2 and 2, because they intersect at 2 and 2. Okay, let's erase this. 2 and 1 and 2. 0 to 2, I mean 0 to 2. So now by creating a vertical strip, let's put it here. This is our vertical strip. Oh no, this is our vertical strip, and this is just equals to x here, and this part will become our y. Here is y. The height of the vertical strip is y, and this part here, let's label this as y equals to 2x and y equals to x squared plus 1. So touching the bottom of the vertical strip, this is our, let's label this as y1 and y2. So y2, so this is our y2, and from this part to this part, from this area to this point, I mean this is our y1. So now we have our values here, and we need to create a vertical shape here. So let me erase this is, and this is the vertical, and this is the our washer method. So washer method has a hole in the middle, so let's put it out here. This will become this and this. So by inspection, this is our area of rotation. So this part will become this is equals to y1, I mean y squared over this is equals to y1. So the differential volume of this is just equals to pi. The bigger part is y1, so y1 squared minus y1 y2, I mean y2 squared So these are, by integrating this, our volume will become pi. By substituting the y1 here is equals to x squared plus 1 squared minus y2 here is 2x squared dx. So now we're ready to integrate this. So pi, then let's expand this first. So this will become x raised 2x squared. Wait, let me put first here. X squared plus 1 times x squared plus 1 comes to x4. Yes, not 2x squared. So this will become x raised to the 4 plus x squared plus 1 minus 2x here. What's that? 2x squared. 2x raised to squared to 2 is just equals to, this will become 4x squared minus 4x squared dx. So now we are ready to integrate this. So pi times x raised to the 4 is just x to the 5 over 5. Oh, we forgot the limits here. Our limits here is equals to 1, 0 to 1, or 0 to 2. Yes, 0 to 2. 0 to 2. And x5 plus x cubed over 3 plus x minus 4. Integral of this 4 is equals to 4/3 of times x cubed from limits to 0 to 2. So by substituting this, our answer will become pi 2 raised to 5 over 5 plus 2 raised to 3 over 3 plus 2 minus 4/3 2 raised to 3 minus 0. So by simplifying this, let me get my calculator. So pi 2 raised to 5 2 raised to 5 over 5 plus 2/3 2 raised to 3 plus 2. This is equals to pi times 166 over 15 minus 4/3 times 2 raised to 3 become minus 32 over 3. So by simplifying this, our answer should be 166 over 15 minus 32 over 3 2/5 times pi is equals to 2 over 5 pi cubic units. So this is our answer for our problem number 1 under washer method. So now let's move on to problem number 2. So let me find first a problem. So now we have our second example for washer method. Now find the volume y equals to x squared plus 3 and y equals to x plus 3. First we need to find the points of the parabola. So y prime is just equals to 2x. So if you keep x to 0, our y will become 3, and by putting 0, 3 here, if our x is negative 1, if our x is, let's say, negative 1, our y will become 4, and 1 means 4, so this is 0, and this is x. If x equals to negative 1, 0, this is 3, this is 4, and this is 1, and this is 4. Our parabola should look like this. You see it? Yes, like that. And now we are going to find the points of our line here. So by doing that, we need to find the both points by doing a tabular table. So if x equals to 0, our y will become also 0, and if x equals to 1, our y will become 4. So our points of intersection is between points 1 and 4. So equals to 1, this is 4. Let's say this is a point here, and this will become our area of interest. Oh no. Our area of interest. Let's make it bigger here. Never mind this part. Let's this part only on the right side. And so by doing this, this equals to 1. This 1. This 1. Then we are going to this part, and our x here, our line is 1 and 4. So 1 and 4. Our area of interest will be here. So guys, it's difficult to use just manually graphing the illustration, so forgive me. And this is our 0 to 3 here, and this is our y. So let's say this is our area of interest. So this is our area of interest. So we need to put a vertical strip here. This is our vertical strip, and this equals to x, and the height of this vertical strip is equals to y, and the point here from the bottom of the vertical strip to our x-axis, let's label this as y2 equals to x plus 3, and this is our y1, x squared plus 3. So this is our y1 equals to, no, y1, that's y1, and from this area here, this is our, oh, this is y2 I mean, and this is our y1. So by doing a circle here, let's put a circle here, a circle here, and let's take this out, our solid surface, or our slice. So let me first illustrate this. So our area of rotation is here between the vertical strip here. I think then from this part to this part, this is just equals to r. Oh no, let's erase that first and let's make the line here. And this is our area. So from this part, sorry, area of rotation again. So from this part to this part, this is our y1, our y1 here, y1, and this is our y2. So by doing the differential volume, this is just equals to pi. I forgot. So pi y squared minus y2, I mean y2 minus y1 dx. The volume of integration is just pi. So let's substitute y squared, y2 here. So our y2, I mean y1, since y1 is bigger than y2 here, y1 minus y2. So pi y1 here is x squared, y1 is x squared plus 3 minus y2 here is x plus 3 dx. Now we're ready to integrate this problem. So pi integration of the pi times, let me mentally solve it, x squared here will become x cubed over 3 plus 3x minus x squared plus 3x from limits to 0 and 4. So pi, so this will become pi by substituting the value 4 to the x. This will become 4 raised to 3 over 3 plus 3 times 4 minus 4 squared plus 3x minus 0. So this will become 4/3. Let me get my calculator here. So 4/3 and 4 is raised to 3 plus 3 times 4 minus 4 squared plus 3 times 4, this is 4, this is 4. So our answer here is pi times 88 over 3. 88 over 3. So by finalizing, our answer will become 88 over 3 pi cubic units. So that is all for the washer method, the disk method, and the shell method. That is all for volume. Thank you for listening, and leave a like, comment, and subscribe at the end of the video. Thank you so much for listening. So welcome back guys. Today we are going to talk about the second method of volume, which is the shell method. First we need to illustrate the our graph. So this is the y-axis and this is the x-axis, and this is our origin 0. So in doing shell method, let's say we have a curve here from points A to B. Now this is our area of interest. Now we are going to put a point here. This indicates x and y, and we need to make a vertical strip. This is not a rectangular strip. Let me try again. This is a rectangular strip. So this is our rectangular vertical strip. So from this point here to the origin, this is x. The height of this is just equals to y, and this is dx. The thickness is dx. So our area of rotation here is parallel to the vertical strip, whether it is vertical or horizontal strip. So in this case our strip is vertical strip, so it is parallel to the strip. So to make a strip here, let's say this is our strip, and we need to put the line here. So this is our tin can, or so this is called the cylindrical tin can. Cylindrical tin can. Now we move this tin can here in the bottom. Let's make it this way. So this is our area of rotation, and the height of this cylindrical tin can is just equal to y. Let's say this is our x-axis and this y-axis. So this height, so the height of this is just equals to y, and this part here is our x, and the thickness of this, let's say this is our vertical strip earlier, and the thickness of this is just dx. So in order for us to solve this, we need to cut it in half. So this will look like this. Let's put it here. Say that. Then this is our y-axis, our y I mean, and this is our dx. Remember guys, this is the vertical strip that we made earlier. So the circumference of the circle is just equals to 2 pi x. X here is our radius, and the limits is along the x. First we need to derive this. So this is the differential volume. Differential volume is just equals to 2 pi xy dx. So x here is the radius, 2 pi x here is the radius, and y here is our height. So the integral of this is just the integral of volume under the shell method is just equals to volume equals integral of 2 pi xy dx. with limits from A to B. So this is our formula for shell method. Now, let's move on to the first example of our shell method. So this is our first example for our number 1 under the shell method. First, we need to illustrate. So let's do that. So this is our y-axis and this is our x-axis. So line here is just equals to line here is just this line, but we need to find its point. So let's do that first. Let's erase this. So to find the points of the line, we need to have a tabular method. Let's say if x equals to 0, our y is also equals to 0, and if our x is equals to 1, our y will become 3. So this is our 2 points. So 0, 0, and x is equals to 1, y is equals to, say, this is 3. Now this is our point, 0, x equals to 2. So our limits here is just x equals to 2. And then what we will do here is we connect these dots. So let me do that, but first we need to make it more bigger. Say this is 1, this is 3, say this is 1. By doing this, this is our line. Wait, let's erase this first. And this is our line. Let's say this is here and this is 3. So our line is now perfect. I'm not perfect, but that is enough to illustrate. So we shade this part because this is our area of interest. So first we need to put a point here that will become our vertical strip, and our vertical strip is from this point to origin to this point is just equals to x, and the height of this is just equals to y, and the thickness of this is equals to dx. So now this is x and y. So by doing the shell method, we need to remember that our vertical area of rotation here is just parallel to our strip. So we need to do that first. Now let me erase that. This is our circle, and let's move this. I think that's good. And this is our cylindrical tin can. So we take this out and we solve its differential volume. So remember earlier, the height here is just equals to y, and the radius of the cylindrical tin can is just equals to 2 pi x, and the thickness here is the dx. So by differential volume is just equals to 2 pi x y dx. So the volume, the integral of our volume here is just equals to the integral of 2 pi, that's 2 pi x, and let's substitute y here to our original equation, which is 3x dx, with limits from 0 to 2. Okay, then we put it here. Volume is equals to, let's take out 2 pi, and then the integral of, let's is equals to 2 pi from x times 3x dx from limits to 0 to 2. So by distributing this, x times 3x is just equals to, let's put it here, 2 pi the integral of, so x times 3x is just equals to 3x squared, because remember the exponent rule, plus when multiplying in an exponent here, we just add their exponent. So from limits from 0 to 2. Now we are ready to integrate our first problem. So 2 pi integration of 3x squared is just equals to 3x cubed over 3. 3 and 3 here we cancel each other, so what will be left is just equals to 2 pi x cubed from limits to 0 to 2. So let's substitute the limits to the x. So our answer here is just equals to 2 pi 2 raised to 3 minus 0, because 0 raised to 3 is just 0 times 2 pi is 0. So let me get my calculator. So 2 raised to 2, 2 times 2 is 4 times 2 is 8. So 2 pi times 8, and 2 pi times 8 is just equals to 16 pi cubic units. So this is our answer for our number 1 problem or example from volume under the line y equals to 3x from x equals to 0 to x equals to 2. So let's move on to our second example. Let me find a problem first. So let's put 2 here. So now this is our example number 2 under the shell method. So find the volume under the curve y equals to 2x squared plus 1 from x equals to 0 to x equals to 5. So first we need to illustrate it here. Let's put it here. So guys, illustration is very important in order for you to know what you need to process. So our x here is 0, and let's say this is 5, and our y here is a parabola. Now we need to differentiate this in order to get its points and its vertex. So y prime is equals to 2x squared plus 1 is just equals to 4x dx. 4x. So if we equate 0 to x equals to 0, our y here becomes 1. So 0 squared times 2 is just 0 plus 1 is just 1. So x equals to 0 and y equals to 1. So this is 1 and this is our vertex. Now we need to find its points. So if it's, let's erase this first. So if now we need to find its points by using the tabular method x and y. So now if x equals to 0 and it's 1, now what if our x here is 1, negative 1, and our y here is equals, and our x here is negative 1, and while we substitute the negative 1 to the x, so negative 1 squared is just positive 1 times 2 is 2, and plus 1, 2 plus 1 is just equals to 3. So, and what if we put here 1 also? It's just the same. 1 and 3. 1 and 3. So we put the point. So this is negative 1 and this is positive 1 from points to 3 here. So we are only concerned about this area, the area from the origin 0 to the point from x equals to 0 to x equals to 5. So never mind this part. So from 0, 1 to 3. So 0 to 1. So this is, let me erase this. Let's put 1 here for the sake of clearer illustration. So 1 and 3. Now we graph. Let's say we put let's put this here. Now this is bounded by the limits of from x equals to 0 from x equals to 5. So this is our area of interest. Now we need to put a point here. So this is just our vertical strip from x equals to from x and y, and from the origin here to the point below the vertical strip, this is just labeled x, and the height here is just equals to y. Now remember the area of rotation is parallel to the strip, so we need to make a circle here. No, not that. Circle there. Then we put this here to make it look like a cylinder tin can. Now we take the cylinder tin can outside. Let's put it here, and this will become straight it. So now we need to cut this off. So this will become this. So the height of this is just equal to this. So this is y, as shown in the illustration earlier. This is y, the height, and the radius of the cylinder is just equal to 2 pi x. And this is the vertical strip, and this is just equals to dx. So now our differential volume is just equals to 2 pi x y dx. The integral of that is just equals to the integral of 2 pi x. Now we substitute y to this original equation, which is 2x squared plus 1. So 2x squared plus 1 dx from limits to 0 to 5. From limits to 0 to 5. Now we are ready to integrate our problem. So let's put 2 pi outside, and then we integrate. So by substituting x and x here to 2x squared and 1, our to make it simply, to make it more simply, our problem here is just equals to 2x cubed plus x from limit to 0 to 5. Now the integration of this is just easy. We need to use the general power formula, which is equals to 2 pi times x cubed plus 1 is just equals to 2x4 over 4. Now by cancelling, x cubed plus x raised to 1 plus 1 is equals to x squared over 2 dx. from limits to 0 to 5. Correct? 0 to 5? Yes. Now, we need to cancel this out. Though what will be left is just equals to 2x over. So this is equals to 2 pi times 1/2 of x squared of x raised to the 4 plus x squared over 2. So to the limits of 5 and 0. So let's do that. Wait, let me get my calculator here. So 2 pi um, 2 pi times 1/2 x here will become 5 raised to the 4 plus x will become 5 squared over 2 minus 0. So it equals to 5 raised to the 4. Let me get my calculator here. So 2 pi times can you see it? So 1/2 times 5 raised to 4 plus 5 raised to 2. You can see it, 5 raised to 2 over 2. So our answer here is 325. So 2 pi times 325 is just equals to 2 pi times 2 pi 650 pi cubic units. So this is our answer for our second problem under the shell method. Now let's talk about the washer method. So welcome back, and today we are going to discuss washer method. So washer method, first we need to illustrate here. As I already illustrate, now we need to put here the points where the area is bounded. So let's say that here, and this is the area of concern, and you put here x and y. So from this point, first we need to make a vertical strip there, and from this point to this point, this is called x, and the height of this vertical strip is just equals to y. And the thickness of this vertical strip is equals to dx. Now what if we have a line here, and this is called, let's call this b, and let's call this y equals to b, and this is our area of rotation. So first we need to put here a circle. So this is, so by doing this we can make a solid shape. So see a circle here, and circle there. Now by taking this out, this will become the shape here, and let's say this is the, wait, take it back, this is the area of rotation, AOR, and this part here is called the x, and this, from this part here to here is just equals to b. So from this part to this part, this is called B, and this is called area here equals to Y. So the differential volume of this is just equals the difference of the bigger area minus the lower area, which is B minus Y, and the formula for that is the differential volume is just equals to the pi of B squared minus B Y squared. So forgot this is our dx here, dx. So by the integral of that is just equals to the integral of B squared pi B squared minus B minus Y squared dx. So now this is our formula, and let's proceed to our equation to our problem number 1 here. So find the volume y equals to x squared and y equals to 2x. So we have two different curves here. The first curve is a parabola, and the second equation is just a line. So first we need to solve the points of our parabola, which is equals to x squared. The differentiation of that is just equals to 2x. Now let's equate x to 0 and y will become 1. Yes, so 0 and 1. X is 0, or vertex here, and y equals to 1. So let's erase that out. But before we erase that, we need to find the other points of the parabola by creating a tabular table here. If x equals to 0, y equals to 1. If x equals to negative 1, our y here will become 2, and x equals to 1, our y here will also become 2. So 1 and 2. So let's do that. So if x equals to negative 1, our y becomes 2, and x equals to 1, our y is equals to 2. So this is our points for our parabola. Never mind this part, just this right side only. So put a curve there. Now we are going to find the points of our line, which is y equals to 2x. So by putting a tabular table, if x equals to 0, our y becomes 2. Or 0, I mean, sorry, 0. And if x equals to 1, our y here become 2. So we have now our points for our line. So 0 and 0, and 1 and 2 here. So by putting that, oh no, 1 and 2 here. So by putting this line, let's make it bigger. So let's put 1 here, 1 and 2. This is our 2. So by putting that, this is our area of interest from limits to 2 and 2, because they intersect at 2 and 2. Okay, let's erase this. 2 and 1 and 2. 0 to 2, I mean 0 to 2. So now by creating a vertical strip, let's put it here. This is our vertical strip. Oh no. This is our vertical strip. And this is just equals to X here. And this part will become our Y. Our here is Y. The height of the vertical strip is Y. And this part here, let's label this as Y equals to 2x and Y equals to x squared plus 1. So touching the bottom of the vertical strip, this is R. Let's label this as Y1 and Y2. So Y2, so this is our Y2, and from this part to this part, from this area to this point, I mean, this is our Y1. So now we have our values here, and we need to create a vertical shape here. So let me erase this is, and this is the vertical, and this is the our washer method. So washer method has a hole in the middle. So let's put it out. Let's put it out here. This will become this and this. So by inspection, this is our area of rotation. So this part will become this is equals to Y1, I mean Y squared over this is equals to Y1. So the differential volume of this is just equals to pi. The bigger part is Y1, so Y1 squared minus Y1 Y2, I mean Y2 squared So these are, by integrating this, our volume will become pi. By substituting the y1 here is equals to x squared plus 1 squared minus y2 here is 2x squared dx. So now we're ready to integrate this. So pi, then let's expand this first. So this will become x raised to 2x squared. Wait, let me put first here. X squared plus 1 times x squared plus 1 comes to x4. Yes, not 2x squared. So this will become x raised to the 4 plus x squared plus 1 minus 2x here What's that? 2x squared. 2x raised to squared to 2 is just equals to, this will become 4x squared minus 4x squared dx. So now we are ready to integrate this. So pi times x raised to the 4 is just x raised to the 5 over 5. Oh, we forgot the limits here. Our limits here is equals to 1, 0 to 1, or 0 to 2. Yes, 0 to 2. 0 to 2. And x5 plus x cubed over 3 plus x minus 4, integral of this 4 is equals to 4 thirds of times x cubed from limits to 0 to 2. So by substituting this, our answer will become pi 2 raised to 5 over 5 plus 2 raised to 3 over 3 plus 2 minus 4 thirds 2 raised to 3 minus 0. So by simplifying this, let me get my calculator. So pi 2 raised to 5 2 raised to 5 over 5 plus 2 thirds 2 raised to 3 plus 2. This is equals to pi times 166 over 15 minus 4 thirds times 2 raised to 3 become minus 32 over 3. So by simplifying this, our answer should be 166 over 15 minus 32 over 3, 2/5 times pi is equals to 2 over 5 pi cubic units. So this is our answer for our problem number 1 under washer method. So now let's move on to problem number 2. So let me find first a problem. So now we have our second example for washer method. Now find the volume y equals to x squared plus 3 and y equals to x plus 3. First we need to find the points of the parabola. So y prime is just equals to 2x. So if you get x to 0, our y will become 3, and by putting 0, 3 here, if our x is negative 1, if our x is, let's say, negative 1, our y will become 4, and 1 means 4, so this is 0, and this is x, if x equals to negative 1, 0, this is 3, this is 4, and this is 1, and this is 4. Our parabola should look like this. You see it? Yes, like that. And now we are going to find the points of our line here. So by doing that, we need to find the both points by doing a tabular table. So if x equals to 0, our y will become also 0, and if x equals to 1, our y will become 4. So our points of intersection is between points 1 and 4. So equals to 1, this is 4. Let's say this is a point here, and this will become our area of interest. Oh no. Our area of interest. Let's make it bigger here. Never mind this part. Let's this part only on the right side. And so by doing this, this equals to 1. This 1. This 1. Then we are going to this part, and our x here, our line is 1 and 4. So 1 and 4. Our area of interest will be here. So guys, it's difficult to use just manually graphing the illustration, so forgive me. And this is our 0 to 3 here, and this is our y. So let's say this is our area of interest. So this is our area of interest. So we need to put a vertical strip here. This is our vertical strip, and this equals to x, and the height of this vertical strip is equals to y, and the point here from the bottom of the vertical strip to our x-axis, let's label this as y2 equals to x plus 3, and this is our y1, x squared plus 3. So this is our y1 equals to, no, y1, that's y1, and from this area here, this is our, oh, this is y2 I mean, and this is our y1. So by doing a circle here, let's put a circle here, a circle here, and let's take this out, our solid surface, or our slice. So let me first illustrate this. So our area of rotation is here between the vertical strip here. I think then from this part to this part, this is just equals to r, oh no, let's erase that first, and let's make a line here, This is our area. So from this part, sorry, area of rotation again. So from this part to this part, this is our y1, our y1 here, y1, and this is our y2. So by doing the differential volume, this is just equals to pi, I forgot, so pi y squared minus y2, I mean y2 minus y1 dx. The volume of integration is just pi, so let's substitute y squared here, y2 here. So our y2, y1, since y1 is bigger than y2 here, y1 minus y2, so pi y1 here is x squared, y1 is x squared plus 3 minus y2 here is x plus 3 dx. Now we're ready to integrate this problem. So pi integration of the pi times, let me mentally solve it, x squared here will become x cubed over 3 plus 3x minus x squared plus 3x from limits to 0 and 4. So pi, so this will become pi by substituting the value 4 to the x. This will become 4 raised to 3 over 3 plus 3 times 4 minus 4 squared plus 3x minus 0. So this will become 4/3. Let me get my calculator here. So 4/3 and 4 is raised to 3 plus 3 times 4 minus 4 squared plus 3 times 4, this is 4, this is 4. So our answer here is pi times 88 over 3. 88 over 3. So by finalizing, our answer will become 88 over 3 pi cubic units. So that is all for the washer method, the disk method, and the shell method. That is all for volume. Thank you for listening, and leave a like, comment, and subscribe at the end of the video. Thank you so much for listening.